Hello friends, in this video we study the characteristics of second order reaction. As far as the characteristics are concerned, there are four characteristics and these are very crucial ones. We shall see one by one. First of all, unit of rate constant. Rate equation for its rate constant K2 this is the expression for a rate constant of second order reaction with equal initial concentration. Now I write the meaning of each term in this equation. K2 rate constant, A concentration, of course initial concentration, T time, what is X? It is again concentration, and A minus X concentration. What I have done only the meaning of each term in this equation. A initial concentration, that means concentration. T stands for time. X is again concentration, and A minus X concentration. And K2 is the rate constant for second order reaction with equal initial concentration. Simplified, this term gets cancelled. What is remaining? This is remaining 1 over concentration into time. If we reshuffle it, then we can also write K2 is equal to concentration raised to minus 1 into time raised to minus 1, or it can be written also time raised to minus 1 into concentration raised to minus 1. Where time t can be expressed in seconds, minute, hour, day and year, and concentration in moles per liter. That we can substitute the value of concentration. What is this? K2 concentration is expressed in moles per liter. Raised to minus 1, and time, if it is expressed, then it will be second units. This can be done in this manner. If we reshuffle it, then we can write this one. Again, it can be written as e raised to plus 1 into mole raised to minus 1 into second units. That means we can write the unit of rate constant in various manners, but generally it is concentration raised to minus 1 into time raised to minus 1. Now turn towards second characteristics. Second characteristics, time required to bring about a definite fractional change is inversely proportional to the initial concentration. What I am saying? Time required to bring about a definite fractional change, that is 50, 75, 25, so on, is inversely proportional to the initial concentration. That means we have to show if half time is taken into account, T50 proportional to 1 over E. We have to prove this equation. Let us start with 50% change. That means time required to bring about 50% of reaction is said to be half-life period. That means we are going to derive the equation for half-life period of second order reaction. I write equation K2 is equal to where K2 is the rate constant for second order reaction. A initial concentration, T stands for time, X amount reacted, and A minus X, it is amount left unreacted. Now we are dealing with 50% change. That means X is equal to A by 2, half of initial concentration, that is half of reaction, that is 50% reaction. What is A minus X? A minus X, the value of X, it is A by 2. Therefore it is A by 2. And T is equal to 1 half. T is equal to T1 half or T 50%. Now substitute all these values in this equation. What do we get? Value of X, it is A by 2, and value of A minus X, it is also A by 2. A by 2 gets cancelled. What is remaining? K2 is equal to now we are interested in finding the value of time required to bring about 50% of change. That is, we are finding T 50%. We separate T 50% is equal to 1 over K2 into A, where K2 is the constant for second order reaction. The equation can also be written as T 50%. Alright, the conclusion of this equation. Time required to bring about 50% of change is inversely proportional to the initial concentration. We can write in another way. Time required to bring about 50% of change is inversely proportional to the first power of initial concentration. Either initial concentration or first power of initial concentration. Third conclusion may be drawn. Time 50% change and initial concentration both are inverse to each other. If higher the initial concentration, shorter will be the half-life period. These are some of the conclusions drawn from this equation. And therefore, from this equation, we conclude that time required to bring about 50% of change is independent of, I beg pardon, inversely proportional to the first power of initial concentration. Now, turn towards third characteristics. Now turn towards graphical presentation. Third one, graphical presentation. Consider this equation. This one. Now reshuffle it. Shift this term to this side. What do we get? K2 into A, this one. This equation looks like y is equal to mx. It's taken along y-axis, time taken along x-axis, and slope of line will be K2, that is a constant multiplied by initial concentration. Now, graph. Times small t along x-axis, and along y-axis it is x over a minus x. It is straight line equation passing through origin because this equation does not contain the term capital C. What I say? Y-intercept. It doesn't have y-intercept. It means that the line passes through origin. That is nature of line will be line slope. Here is equal to, this is the slope of line, K2 into U. If slope is known to you, then we can easily find out the rate constant for second order reaction. That is K2 is equal to slope m over initial concentration. Once slope is known to you, we can find easily the rate constant for second order reaction from graph. One more way of graphical presentation. Consider the equation of rate constant for second order reaction with unequal initial concentration, and this one. This where A is greater than. Now we are going to reshuffle this equation. If we reshuffle it, this factor is taken to this side. What do you get? Log of if the shifted here, K2 into A minus B over 2.303 into T. Is that it? It's shifted here, we get this. Now, speed this term. Log B over A plus log this one. shifted to that side. What do you get? This is the final step. This term plus it minus it log B over. This is the equation of straight line y is equal to mx plus c. That means this term is taken along y-axis, along x-axis compared time is taken, and this will be the slope of line. And this is y-intercept. Y-intercept is negative. So proper care should be taken in representing this term in the graph. Right? Now I plot the graph. Along y-axis, log a minus x over b minus x having base 10. And along x-axis, this tan theta. The plot the graph of this straight line with positive slope and having negative intercept. That means nature of line would be like this. This part minus log of b over a, that means y-intercept. The line cuts the y-axis at this point, minus log of b over a, and slope is equal to k2 a minus b upon 2.303. If slope is known, then we can write the value of weight constant. How it can be calculated? Slopium is shifted 2.303, and this one a minus b is equal to rate constant of this reaction. These are the graphical representation of second order reaction with equal and unequal concentration. Both are straight line, but equal initial concentration and the line passes through origin. In this case, unequal concentration, the line is having positive slope and negative intercept. Therefore, the nature of line will be like so. Now, last characteristics. Last one. When one of the reactants is in large axis, then second order changes to the first order. What I am saying? When one of the reactants is taken in large axis, then second order changes into the first order. Now we have to prove. Equation K2 is equal to this one. If A is greater than B. Now, A is the initial concentration of first reactant and small b the initial concentration of second reactant. what is condition? A and B. A is quite too large as compared to small b. If we apply the condition, we impose the condition, then we can get A minus B. How much? A is too large and B is too small. Each subtraction will be near about small. A minus 6. A is too large, B is too small. And point to be noted that X is the amount of both the reactants which is reacted from each reactant. It means that X is too smaller than A and again too smaller than small a. If it is the condition, then A minus 6 should be equal to small. Now substitute one more. It is. Now substitute the condition here. K2 is equal to 2.303 T. What is A minus B? It is near about to small a. Log B. What is A minus 6? Small a. A over B minus 6. What I am doing? I have substituted the values of each term here. This A and this A goes out, and if this initial concentration is shifted here, what do we get? K2 into small a is equal to 2.303 T log of B over B minus 6. Rate constant multiplied by initial concentration, this K dash, 2.303 T log of B over B minus 6 to the base 10. Now what is this? If we memorize the equations, then it is the integrated rate law for first order reaction. That means it is the first order kinetics. Initially, we had this equation. After imposing the conditions, that is one of the reactants is taken large excess, then second order changes into the first order. This equation I have written, applying the condition, A is too large, B is too small, and again X is smaller than A and B. This one, the terms are written here, we separate, we get this one. That means what we have written, when one of the reactant is taken in large excess, the second order changes into the first order. These are the four characteristics of second order reaction. Thank you very much for being with us. Thank you very much.